Hello everyone, my research is on control of continuum robots, which we will briefly call them CRs. Continuum robots have gained significant attention during the last decades. Although there are many advancements in development of continuum robots, control of CRs still poses several challenges due to their limited actuation channels, hyperflexibility of their structure, and their nonlinear model. CRs are typically employed in confined spaces such as organ cavities or vessels inside human bodies, where usual sensory visuals are not compatible with or due to associated uncertainties. Usual position of force sensors are not safe to be integrated into the system. And considering that such work area are mostly equipped with imaging modules, we will find image-based control strategies of the promising controller for such environments. In this paper, we have developed two controllers, one to control a single CR and the other one is to control a cooperative set of CRs, also called CCRs. Let's start with cooperative CRs and you will see why we need these two controllers. A CCR configuration would be formed by attachment of a supportive CR to an operative CR. A push from the supportive CR will help operative CR reach a target point outside its reachable space. There are multiple reasons motivate us to use this configuration. The foremost is when interested to reach a point outside the reachable space of the operative CR. To perform a positioning task using this configuration, we first need to manipulate a single CR to the target position, which can be located in a large distance from the initial position. Then in the proximity of the desired point, the CCR configuration would be formed, allowing for fine-tuning. Such scenarios usually need a small displacement. So for the first part, we need control of a single CR, and for the second part, we need to develop a controller for CCRs. Literature includes various research on control of a single CR, but a comprehensive control study of a single CR is missed, and also there is no control on the CCRs. To develop our controller, the first thing we need is the robot model. In general, there are two approaches: the quadrilateral theory, which is an advanced accurate model resulting in a nonlinear set of differential equations, and the second approach is constant curvature, which is usually used to model CRs with an acceptable accuracy in absence of forces and moments. If looking at the picture on the left bottom corner, you will see a closed chain has formed between the two CRs in a CCR configuration. This closed chain forces to use quadrilateral theory, since at the interaction point of the two arms, there would be internal forces and moments. One big challenge of control of CCR is the Jacobian that needs to be calculated numerically. So it might be ill-behaved and associated with computation cost. So in the controller, we need to care about this part. To control a single CR, we developed a model-based visual predictive control strategy, which gives us the advantages of both model predictive and visual serving control approaches. The controller enables dealing with different types of constraints, which is very beneficial to the control purpose. To control a CCR, we introduce a scaled and non-dimensional SND IBBS and also a novel switching control strategy between standard and SND IBBS. SND IBBS is based on integration of SND robot Jacobian into the controller. As part of our model needs to be calculated numerically, SND Jacobian helps a lot in the convergence. Also, another challenging step here was the proof of stability. You can see that the two conditions that lay upon stability criteria iteratively force them into the system. To investigate the performance of the controller, first we showed that both controllers work well in the presence of actuation and imaging imaging noises. We showed that a VPC can handle various types of constraints, demonstrated that in a higher prediction horizon, accurate estimation of depths would have a more significant effect on the error deduction. We illustrated that increase of the prediction horizon results in longer convergence and smoother trajectories. In a comparative study between performance of VPC over IBBS, in absence and presence of constraints, we showed the superiority of VPC. For CCR, we also compared the performance of the switching approach with the subsystems. The switching approach worked the best among the three controllers, meaning that the trajectories are smoother and the convergence happens sooner. SND assembly formulation was very interesting in the beginning of the manipulation, where there is a large amount of error. Assembly IBBS, where there is a large amount of error, assembly IBBS subsystem quickly reduce that error. But when we have a small errors, its performance drops. So in the combined approach, we use assembly formulation for reducing the error to a threshold, and then switch to the standard formulation to get rid of the remaining small amount of error. Finally, we showed that the controller works well in practice. Thank you so much for having me. I would be happy to answer your questions.
So Dr. Gutierrez, do you have any questions?
Yeah, so I would like to know some of the applications of this one, like do you have some kind of equipment that already been possibly applied this technique that you developed and compared it to this controller?
Sure. The application of the controller, the switching approach, is when we have systems with computationally expensive models, such as Continuum robots, and we especially developed this controller for Continuum robots that their models consist of a set of nonlinear differential equations, and we need to calculate that numerically. And for VPC, we work with them when we need to meet different types of constraints. And regarding the application of the entire system, CCR configuration, that is where we want to reach to a point that it cannot be done by use of one CR, or we want to do a task that cannot be done with one CR, and we need the cooperation of these two. For example, if you want to change a mitral valve in cardiac, one approach is that to manipulate the single CR to the proximity and then use the CCR to increase the stiffness and do the task with the set of CRs.
Thank you.
Thanks.
Dr. Gorbet, do you have any questions?
Yes, thank you for the presentation. This is a little bit outside my field, so my question might be a little uneducated, but I was interested in your experimental validation, because you've got a really nice complex models that's been able to verify some of your controls, and then obviously you have to validate it. But when I'm looking at the picture, and obviously this is to apply in blood environment in a way, it seems like it's all done in air because I don't see any fluid around it. So how is that, how can you validate something that's, supposed to happen in blood and something that is done in air, in air basically? And would that affect, that's likely going to affect some of your control because you're trying to move things around.
Yeah, exactly. The experiment and the verification has been done in the laboratory experimental workspace, and not in a real phantom. I mean, not in fluid or in blood or in a real cardiac. And the reason is that this is the first to work on control of a single CR and CCR for large displacement. So we as the first step, we need to prove the concept in the laboratory setup, and then we can work on improvement of the imaging module, and then go and do it in cardiac. There we need to use the different imaging filters. We need to employ another imaging module, and then but the controller would be applied in that condition. And the experiment and the real phantom would be the next step of the work. It is one of the steps we consider for the future of the project.
Okay, and so if I have a minute, just to make sure I understood. So basically, when you also build your model, that was also an aspect that you thought about around some of the potentially the fluid mechanics and the friction that might affect the, okay, but I wanted to make sure I wasn't 100% sure. Okay, great, thank you.
The robot we use the experiment on it is an ablation catheter. It is a real ablation catheter, which is commonly used in medical in surgery. And as our model is robust, we show that through handling different types of uncertainties and different types of noises, that would be able to handle uncertainties because of the friction and because of the model. Since friction can be considered as an uncertainty with the robot model. So when our control is robust, that means that it can handle those types of uncertainties. So we already are carefree about that part.
Okay, great. Thank you so much.
Thank you.
Somayeh.
Thank you.